So we're continuing with our regions of integration being non-polar rectangles, even though we're in the polar coordinate system. So this time we want to look at this zone. It's still the same two circles as the last two pieces, but we're going to look at this little section of it. Okay, so, and it's a different three-dimensional object above. Remember, these are a ceiling, some kind of three-dimensional surface up above this piece, right? So you want to see what shadow, if you will, this piece casts back upwards onto the ceiling, if you want to think of it that way. Okay, so let's find the double integral. So it's x plus y. X is r cosine theta plus r sine theta times r dr d theta. Oops, and I'm going to change those to colors. So dr d theta. All right, we already know that this is theta equals pi over 3. We've already found that. So we actually know both of these because we know that this up here is theta equals pi over 2. Right? So we know we're going from pi over 3 to pi over 2 for our two theta values. No problem. Right? And again, this was x, this was y, this is dA. Just in case you lost sight of that. Okay, what about the r's though? All right, so let's imagine a spoke coming up from the origin, and let's try to do it in the most useful way. So it's going to come through this blank white space and hit this and then hit this. Okay, so first it's hitting this ring, which is 4 cosine theta. And then it's hitting this ring, which is 2. So there we have it. Okay, so now we just need to integrate this. Now notice, there's theta in here all over the place. So you cannot use our trick, right, and get rid of the thetas. Just can't do it. So you're going to have to actually integrate this. All right, so, and you have to do r first. Because of the cosine theta right here, you actually have to go in this order. So we'll just make a little note. Right? We have to do the dr first. We have to, because the r value has a theta in it. So we definitely have to go in dr d theta order, and we have to do dr d theta. We can't use our trick of making it disappear. Boo. Okay, well, let's do it. So this is going to be the integral. I'm going to distribute, actually, I'm going to factor. If I look here, this has an r in it and this has an r in it, so I'm going to pull an r out and make it r squared because I already have an r out here. So I'm going to take the integral from pi over 3 to pi over 2, and then make it r squared times cosine of theta plus sine of theta dr d theta. And yes, I lost one of my integral symbols. It's because I hadn't decided if I was going to integrate or not, but I decided not to. All right, so this is 4 cosine theta and 2. All right, now I'm going to integrate this. So this will be 1/3 r cubed. I'm just going to write the 1/3 out in front. Pi over 3 to pi over 2 r cubed. R is going from 4 cosine theta to 2. And then it's just multiplied by cosine theta plus sine theta, because that doesn't have any r in it. I'm not worried. D theta. So now I'm going to stick 2 into this, and that's 8. And then I'm going to stick 4 cosine theta into it, and that's 64 cosine cubed. So this whole thing becomes 1/3 integral from pi over 3 to pi over 2. And then it's 8 take away 64 cosine cubed theta times cosine of theta plus sine of theta d theta. And we're just going to make Maple do that. Right? We're not going to bother. This is what Maple is for. All right, so let's go grab it. And there you have it. So you can see I put in the original and then I put it in after I had integrated. That way I can check my by hand work and make sure I integrated correctly, which I did. And I get that the answer is 1.2099 or 1.21. And there we have that. All right, so let's do the last example. Let's push. So this particular piece is a rose. So let me draw that picture for you so you can see it in Maple. One second. Here it is in Maple. So we have this beautiful rose, which is the 2 cosine of 4 theta, and then we have that circle, which is the r equals 1. All right, so I cheated and I printed it and I put it on my paper. There we go. All right, so we want all of the regions. So to find the area inside that lovely, lovely rose, but outside r equals 1 is a lot of places, right? Because there are so many sections where that is the case. But of course, we're trying to find area. So we're not even interested in a three-dimensional object above this, right? If we're going to find area, then we know that the integrand is 1. So this is going to be a little bit simpler if we are smart about this. Okay, so let's first think about area. So if we want to find the area, that is the double integral over the region of 1. Right? We learned that that is the case. Okay, so now we want to set this up, but we want to be smart about it. So we know that it's 1. 1 wouldn't change. I know that this will be easier in polar. Hello, this is a polar graph. So I know it's going to be r dr d theta. No problem there. Now, here's where you want to get smart. You don't want to do all of this because that would be super irritating. What you want to do is find just one piece of it right here. If we can just find that one piece, then we can figure out all the rest of it. Because this is area, it's all going to be identical. This is automatically symmetrical. So I just need to find this section, and I think there's 1, 2 of those per petal, and there's 1, 2, 3, 4, 5, 6, 7, 8 petals. So what we're going to do is we're going to multiply by 16, right, due to symmetry, and we're going to go from 0 to something. Right, that's the tricky bit. We got to find what this angle is right here. We need to know what that angle is. All right, and then the r, I can actually do r right now. If I make a spoke come out, it's going to hit at that ring of 1, and then it's going to hit at that petal. So it's going to go from 1 to 2 cosine of 4 theta. So actually r is pretty easy in this case, right? So, but this is by symmetry, right? We're doing this from symmetry rather than doing, well, it's actually the 0. It's the 16 and the 0 that are coming from symmetry. So I should really write that on the bottom. One second. All right, there we go. Use symmetry, right? 0, and that's how the 16 happens. All right, so all we have to do is find where they touch. Where is this ring equal to that petal? So that's where these two r values are the same. So to find theta, we're going to find the intersection. So let me just write it over here. So we need to know where 2 cosine of 4 theta is equal to 1. Okay, so that would mean the cosine of 4 theta is equal to 1/2. And we've already run into this before. That happens at this angle. 4 theta is equal to pi over 3, right, because of the unit circle. And therefore, theta is equal to pi divided by 12, because you would multiply both sides by 1/4, and 1/4 times a third is 1/12. Sorry, not a half, a 12th. All right, so then we're going to go up here and we're going to put pi over 12. All right, now again, theta is in here, so we cannot use our trick and all that stuff. We have to do this. So, and we have an r, right? Don't lose sight of the r right there. So the integral of r is 1/2 r squared. So this is going to be 16 integral from 0 to pi over 12, 1/2 r squared from 1 to 2 cosine of 4 theta d theta. All right, well, 16 and a half makes 8. So that's really 8 integral from 0 to pi over 12. And then I'm just going to plug in this. So that's 4, because 2 squared is 4. So 4 cosine squared of 4 theta. Right, you square the 2 and you square the cosine, not the 4 theta. That's an angle, so it just stays there. Minus 1 d theta. Right, remember the half got pulled out. The half came out over here. So that's why I'm not looking at the half. I'm only looking at the r squared. And then we just make Maple do this, right? We don't have to do that by hand. This isn't Calc 2. So Maple. Let's see what we get. And here it is. So I put in the original integral that I developed with the 16r. And then I also did it after I had integrated to double check my work, because then I know I integrated correctly because these two answers worked out to be the same. So as long as my original write-up was correct, then so is my solution. All right, so this actually equals exactly square root of 3 plus 2 pi over 3, or it's approximately 3.826. Now, don't lose sight of the fact this was area. So if we knew, let's just note x, y in, I don't know, meters, just for the fun of it. So if that's the case, and our coordinate axes are in meters, or r is in meters, you could say r is in meters. I guess I will say it. I'll say r in meters, because if r is in meters, that means x and y are in meters. So that would mean that this is meters squared, because this is an area, right? Meters squared. This was not a volume, because we were integrating a constant. Well, actually, we were integrating 1, that's why.